Hello, my name is John Moyer, and I want to welcome you to the NIH Office of Disease Prevention's Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions to promote the use of the best available methods and to support the development of better methods. Before we begin, I have some housekeeping items. You can submit questions during the webinar via the chat pod. You'll need to open the pod by clicking on the chat icon located in the lower right-hand corner of your WebEx window. Please direct your questions to all panelists. We will open the floor to questions that have been submitted via WebEx at the conclusion of today's talk. The slides and video recording will be posted on our website, prevention.nih.gov/mindthegap, in approximately 2 weeks. You will receive an email when they are available. Lastly, we would appreciate your feedback about today's webinar. Upon closing the WebEx meeting, you'll be prompted to complete an evaluation. We would appreciate your feedback as it will help us improve this webinar series. Dr. Murray is not able to attend today's webinar, so allow me to introduce today's speaker, Dr. Timothy Wimkin. Dr. Wiemken is the Senior Director of Clinical Epidemiology for the Pfizer mRNA vaccine platform. His work focuses on data-driven approaches to solve pressing clinical public health issues. Prior to joining Pfizer, Dr. Wiemken was Associate Professor of Medicine in the St. Louis University School of Medicine, Department of Internal Medicine, Division of Infectious Diseases. In addition, he was Director of Infectious Diseases Epidemiology at SSM Health, St. Louis University Hospital. He has over 200 peer-reviewed publications, book chapters, and scientific reports in the area of infectious disease prevention. It is my pleasure to welcome Dr. Wiemken.
Excellent. Thank you so much. Thank you all for joining us today. We have a pretty intense overview for a very short time, so hang on with me and we can have a great discussion at the end. All right, so just a couple of housekeeping items on my end. As Dr. Moyer mentioned, I am an employee and shareholder of Pfizer currently, less than a year in, but I'm still also faculty at St. Louis University. This presentation is not sponsored or affiliated with my employer. Everything is just my opinion and my thoughts on the subject matter. And probably more importantly, I'm not a theoretical statistician or a mathematician or a computer scientist. I'm an applied epidemiologist. So my approaches and my thoughts on this topic are really in the applied nature. So we're just going to tell a story today. I like movies a lot, so we're just going to kind of treat this like a movie here. And also, we're going to focus on really one area of machine learning. We're going to touch on some of the other areas, but we're really going to focus on supervised machine learning, and I'll tell you what that is in a little bit. But that's just for the sake of brevity and the timeline that we have. And really, supervised machine learning is really what most people think of, or what most people mean when they mention machine learning. All right, so Act 1. Alive. Machine learning models are not alive. So what is machine learning? When we talk about machine learning, it's really an umbrella term, which is an umbrella term to comprise several algorithms that allow some model to be created, typically to predict an outcome. Again, that's the supervised machine learning part, is the prediction of some outcome of interest. A lot of times you hear about people mentioning, ML and AI, machine learning and artificial intelligence. And they kind of use those terms synonymously. They're very much not synonymous. Machine learning is not artificial intelligence. Machine learning as an umbrella phrase is really a single means of a lot of different methods to be able to achieve artificial intelligence. And you can argue with everybody of whether or not we have artificial intelligence currently or not. I won't go there. So these are kind of the three tiers of machine learning that we really have right now. There's some other kind of subsets, but this is really kind of the three areas. There's unsupervised learning, supervised learning, and reinforcement learning. Unsupervised learning is focused on just looking at a data set, no outcome, no predictor, nothing like that. Just here's my data. Try to figure out what the patterns are in these data, not in reference to any outcome, but just what are the patterns here. And this is like cluster analysis, principal components analysis, data reduction techniques to look for just general patterns in an entire data set. Supervised machine learning is we do that same thing, but we want to know the patterns and how they're associated or in reference to a particular outcome of interest. Can we separate out these groups of patterns and how they're linked with a particular outcome or not? Reinforcement learning is more of a novel approach that isn't interested in one particular outcome, but a series of outcomes. So we want to assign weights to events that happen. So ideal scenario of this is like a video game. So if I'll show my age, like Super Mario Brothers, the greatest video game ever made. When you're playing this game, you jump and then you have some outcome and then you hit the block and you get a coin. Well, that coin reinforces some outcome. When you get 100 coins, you get an extra life. So all of these sequential outcomes and how those impact some eventual endpoint. All right, so in machine learning, we also have a lot of issues in terms of terminology. When you're starting to learn these types of things, it can be really difficult to just be like, what are these people talking about when I'm reading this study? Like these terms make absolutely no sense to me. And that's because it's really derived from computer science. And the language of the terminology is a little bit different because of where it's sourced from. So I've done a little bit of linkage in terms of terminology here, at least with what we'll talk about in this presentation today. So in our traditional kind of frequentist biostatistical thing, we have outcomes or a dependent variable and a response variable, kind of those things are synonymous. In machine learning, we call that a label oftentimes. Now you'll see more people mention it as an outcome. In fact, a lot of authors now will say, don't even use the term machine learning, use statistical learning, because biostatistics and machine learning have become so interlinked that it's hard to really say this is machine learning. What's really, we also have confidence intervals and p-values and different things in a machine learning model. So you do see some overlap in usage of these terms sometimes. In biostats, we have independent variable, predictive variable, exposure, covariate, and that's great for biostatistics because of a lot of the assumptions that we have for different models. Independent variable, for example, the variables in the right-hand side of our regression model need to be independent of each other. It's part of assumption of these models. In machine learning, we call those features because we don't really have those assumptions that we have to meet. So you won't really see these terms necessarily used in machine learning so much. In biostats, we may fit a model, estimate a model. We call that training or learning in machine learning. Biostats, we mention regression a lot of times. It's logistic regression to do whatever. We want to explain, the impact of age on lifespan or something. In machine learning, we also use regression, but that's in supervised machine learning, regression is used when the outcome is continuous variable. In the context of a categorical outcome, we use the term classifications. We're trying to classify things into this group or that group. As I mentioned before, unsupervised machine learning is clustering PCA data reduction techniques. Those are kind of what we mean by that. And then biostats, you might have some model options like a logit link in a regression in a GLM or something. In machine learning, you have more advanced options, and we call those hyperparameters. And we have to tune those hyperparameters to be able to make the model better. We'll see how all of this works later. The question that I get more than anything is machine learning better than traditional biostatistics? And in the context of supervised machine learning, for most use cases, when you just have the same data, the answer is no. It's really probably not. If you have this set of data from an electronic health record and you're trying to predict no-shows or something in a clinic, and you have the typical EHR data, you use logistic regression or you use a deep neural network, you're going to get the same result. The algorithm itself is probably going to give you very limited, if any, sometimes worse, ability to predict the outcome than a traditional model. And these more complicated models can just be more difficult to explain. Now, what you'll see is machine learning shines in certain areas when you don't have that typical data set, when we start really violating the rules of traditional methods. And again, we talk about machine learning as this new fancy thing. But the reality is all the traditional methods can be machine learning. Like you can create a predictive model using logistic regression, and that's machine learning. I mean, you train your model, you test your model, all the same approach. It doesn't have to be a random forest or an artificial neural network or any of these fancy things. It can be logistic, it can be linear regression. And that's oftentimes what happens because you want a simple model to be able to predict some outcome. And if you have enough data, if you have enough good data, then it's going to be probably just as well. Now, when machine learning is going to shine is when you have, again, violations of our traditional regression assumptions. So how does all this work? So a model is going to get trained, and we're going to create this model on a subset of your data set. We call that the training data. And this algorithm, the algorithm that we use to create this model, is going to recognize the patterns in this training data set in relation to some outcome of interest. So our training data set is going to have the outcome. It's going to look for patterns and see how those patterns, fall within, this group or this other group or whatever it is. Then, once this model is created or trained, a new data set, testing data set we call it, is supplied to this trained model to get some prediction. It's just like a traditional predictive model if you've created a predictive model in logistic regression or whatever. Same thing, just different algorithms. So this is what it might look like. So here's a example data set. So you can see the label here on the left, and this particular data set I created, it's looking at influenza vaccine uptake by county in the United States in 2020, 2021. And the label 0 means that the county had less than 50% vaccine uptake during that season, and a 1 means they had greater than or equal to 50% uptake during that season. You can see some other variables here. We have the county level area deprivation index from 2020. We have the region of that county was in, the census division. And then these columns are the University of Wisconsin county health ranking for these particular, like the life or quality of life different rankings. So it's ecological data set. So the first thing we have to do is split this data set into two chunks. One is a training data set and one is a testing data set. And you don't want these, you want these to be as random of polls as you can. So I don't know if that zoom in helped at all. But the question is, how much data do you want in your training data set and how much data do you want in your testing data set? The typical approach is about 80% in the training and 20% in the testing. You see maybe 75, 25, or some other value. Now, the important part is you want the most data in training because you want to create a model that has seen every possible pattern that's going to be available in any other data set because you want it to be generalizable, right, to anything. As much as possible, you want it to be generalizable. And in order to be generalizable, it has to have seen all the patterns before. If it hasn't seen all the patterns before, then it's not going to be able to identify them later and predict correctly. So that's why we have much more data in our training data set as in our testing data set. Now, the next thing is we take that training set and we build the model. Now, the issue, depending on the model you select, there's always, again, these hyperparameters, all these options for different models. This is code that was written in R, if you're an R user at all. And every model is going to have a different number of hyperparameters, and they're going to take some value. It could be a numeric value, it could be some logical value. It just depends on the model. This is kind of where the art of machine learning is going to come into play a lot. An example here, I created a neural network, artificial neural network, one type of machine learning that, a fancy version of this is going to be deep learning. You've probably heard of deep learning before. Deep learning is just artificial neural networks that are a little bit fancier. There's two options, two hyperparameters in this particular model, decay and size. And I don't know what these numbers are going to be. So what I'm going to do is create a grid that is going to be assessed in the model, and it's going to take all of the particular combinations of these two hyperparameters into account and find the best one, essentially. Build this model and find the best hyperparameters. And the way it does this is I create this grid, and I'm going to set 3 values for decay and 4 values for size. And then when I train my model, this is, I think, using the caret package in R, there's so many good packages depending on the approach that you use. If you're a tidy person, you can use tidy models and all these different things. So I'm using a neural network, and I'm using tenfold cross-validation. So if you use cross-validation before, it's a typical approach in biostats. It's going to take a sample of the data set, create the model, take another sample, 10 samples, and then do all of these things. So in each one, it's going to create a model with every combination of all of these different hyperparameters, and then spit out the best accuracy. And this is what you get from this model. So it's going to show, the 4 different sizes with the single decay value and then the accuracy for each one. And then the same 4 sizes with the next decay, the same 4 sizes with the next decay. And then it says the best model is the one where the size is 3 and decay is 0.01. So that's what I'm going to use. So that's my final model. That's my trained machine learning model. That's all it is. So I take that model and I do this one line. I say, predict my neural network. Again, if you go back here, you see that I called this trained model NN. So I'm saying predict NN using my new data, my testing data that I had split out before in the prior thing. And type equals prob just says, give me the predicted probabilities of each class. So what does this model think that this particular patient, this particular county is going to be high or low influenza vaccine? So each of these items here on the left are going to be the rows in the data set. In R, you get an assigned number to each row and it stays there for the life of the data. So low means that's the prediction for less than 50% vaccine uptake, and high is greater than or equal to 50% vaccine uptake. And then the number here is the probability multiplied by 100 to get the percent that the model predicts it's going to be. So this county, row 4, whatever county this was, it thinks about 91% probability that that's going to be a low vaccine uptake. And then you can go down here and see the rest of them. So what do you do with that? So you have to, probably the best way to do it is to find some cutoff. And usually there's a cutoff of 50%. So if you say a county with greater than 50% probability from the model, we're going to say the model's predicted that as high. So if the high column was over 50%, we give it a 1, otherwise we give it a 0. And that gives us a binary endpoint here. And that's going to be this contingency table here, machine learning called a confusion matrix. The rows here are going to be yes, no, if the model predicted high uptake or low uptake, again, cut off at 50%. And then the reference is going to be in the testing data set, what actually happened? Was it high or was it low? So you can compare what the model predicted versus what actually occurred, and then compare those to get your different statistics. Typical diagnostic accuracy in epi and machine learning, same thing. Sensitivity, specificity, positive, negative predictive values, and accuracy. So accuracy we use a lot. And here, 22%, 23%, that's not so good. Important thing when you're classifying, this is very, very, very important. Now, if you don't get anything else from the presentation, beside the memes are very important to know. Know that if you're classifying something, you need to look at the balance in your outcome. So anytime you're looking at a model, we run across this a lot, and when it's in the hospital, people trying to, sell machine learning models, and you have to know that when the model was trained, was the outcome balanced? So here, our outcome, low vaccine uptake versus high vaccine uptake, yes, no. You can see that we had about 30% of the counties had a high uptake and 70% had a low uptake. That's imbalance. You want about 50-50. If you don't have balance, then you can run into big problems. So let's take an example. Community-acquired pneumonia, hospitalized patients with community-acquired pneumonia, mortality. The high end of mortality for a pneumonia patient in the hospital is about 10%. So if we're trying to predict mortality in hospitalized patients with pneumonia, and we just say, here's our big data set, everybody, 10% dead, 90% alive, you can just say everybody's alive. And you're actually going to be 90%. right? Because by definition, you can only be wrong 10% of the time. So you've created this highly accurate model, but it didn't do anything. It didn't do what you wanted it to do. It just predicted everybody was alive, which still looked great. So that's what this balanced accuracy shows you. If there's imbalance, these are going to be different numbers. And you need to account for that. So really in your training data set, you need to have a balanced data set. So how do we do that? Here we were, essentially 2/3, 1/3. So you can do two things. You can downsample your training data set. So after you've split it out into training testing, you take your training data set and you look at the outcome. And here we would say, the 722 highs, well, let's randomly sample 722 lows. And then we have a data set that is 722 high, 722 low. And then you retrain your model and get your outcome. You can also use the SMOTE sampling. There's other techniques. SMOTE is synthetic minority oversampling technique. So it looks at the high group, the minority class, which is the one that has fewer frequency, and it's going to make up fake cases that have the same types of patterns to increase oversample the minority class to get about 713 highs. And that works pretty well too. There's plenty of research in that area. So I took that training data set and I downsampled it. So I had 722 in low and 722 in high. I redid the exact same thing that I did in the prior slides. And here's my new contingency table. And you can see that my accuracy actually went up to about 30% and balance accuracy is about the same. Now, accuracy is not everything. Sometimes we, just like in diagnostic medicine, you might be more interested in sensitivity or specificity or positive negative predictive value, and you can look at those and focus on those instead of just looking at accuracy. Now, when you're creating your model, an important thing to know is it good outside of the performance? And there's this concept in machine learning called the bias variance trade-off that everyone always talks about. And everybody usually says, machine learning, you want more data, better, which is true, but you want more data that's good data. You don't want noisy data. Noisy data are bad, always, in any statistical modeling or machine learning modeling. So the bias in machine learning means if you have high bias, you're not predicting what you want to predict. You're just like down here in this target. You're predicting consistently, but you're consistently wrong. And that's not good. And that's usually because you didn't have enough data that were actually predictive of your outcomes. It didn't recognize the patterns that it needed to recognize. And you can see that here, this would be a high bias, also called underfitting, where, if you have a regression line here, the line is there, but it doesn't really fit the data so well. It doesn't explain the trajectory of the data as well. Now, you can also have high variance, where you have too much noise in your data, and you essentially memorized the training data set, which is going to look like you have this super accurate, high accuracy model in training, but when you test it, it's always going to be terrible. It doesn't generalize at all, because you have all this noisy data that's very specific to your training data set. And therefore it's memorized it. And this would be on the right example of that, where, you could say this is just nonlinear relationships, but it's really just memorize the training data set. And then when you put new data in there, that's not exactly the same as the training data set, it's going to fail pretty miserably. So you got to have that mix between complexity. You want enough data, but it has to be enough good data. But just like anything else in any statistical modeling. All right, so how do we get good data? How do we get all of these data? Well, we can transform them. So in machine learning, it's called feature engineering. So we get data, but we can also take the data that we have and make more data from it, because individual data elements may increase the prediction of your model. Again, we want more data, but we don't want to overfit. We don't want too much noisy data. So how do we do this? So an example, dates. Let's say we have one date column in our data set. We have this individual column that's just a date. So we can take that date and create a lot of other stuff from that single date. And all these other things may actually increase the predictive power. That date may not be enough to explain the outcome or look at the patterns of the outcome. So example here, I've extracted the month, the frequency of that month in the data set, the year, the frequency of the year, the day of the week, the frequency of the day of the week, the quarter, the frequency of the quarter, the season, depending on where you're at in the world, that can obviously change. The days since some index point here, the days since the World Health declared COVID pandemic. Every month has a different number of days, so the proportion of time that that particular day is through the month. All these different things, and then you can add all of these things to the model. But again, you have to be careful. You have to select your model appropriately, or use some data reduction techniques like lasso, some penalization thing. You can use genetic learning. You can use something. Just don't use stepwise regression to try to reduce the number of data elements in your data set. You need to reduce them to a useful data set that's not too noisy. But selecting a model can be helpful too. Models like tree-based models, random forest, cat boost, XG boost, these types of boosting models or bagging models, decision trees can limit overfitting in your model. And then if you have enough data, it can also help with the underfitting situation. So as far as sample size for these models go, there's some research in the area, but in general, it's based on being able, the computer to be able to recognize the patterns. So if you think that there's enough patterns in 20 mice, that's fine. I mean, you don't have the limitations of false positive rates and issues with extensive confidence intervals because of small sample sizes and all these things in machine learning. You can create a machine learning model in as small of a data set as you want, but you have to know that it may not see all the patterns, so it may not generalize outside of the patterns that you supplied to it. Another big issue in machine learning is missing data, and we know that this from traditional statistics that you can impute, but you can only impute if data are missing at random. And the reality is data are never missing at random. Unless you made it missing at random, it's not missing at random. So then imputation becomes difficult, but you can work with some other options here. So example here, I actually here I imputed, made some missing data at random in this length of life ranked column. So here's what I can create from this. So this label column or length of life is this column here. So you can create an indicator. Was it missing? Yes or no? That's kind of a typical first pass. And then you can impute with a mean, or you can impute with a regression model. There's random forest imputators now, so you can use machine learning to impute the data. But you can also add other columns. So how often is this particular value missing within a subgroup? So that's when this essentially can be as big as you want. So you look at all the different subgroups of your data. So like within the southern region of the United States, how often is length of life missing? Well, 33%. But what about the census division? It's going to be a different frequency. So all those, again, can add predictive power to your model. Assessing randomness, missingness in data is a pretty complex topic. It's hard to define, especially missing completely, not at random. You have to actually collect the missing data to be able to figure out what's going on. But in general, missing completely at random is what you want. Missing not at random is going to be like if the missingness is associated with some other variable in your data set. So there's a lot of statistical methods to use to define if there's missingness, but there's R packages. Mice, I think, is a great R package for assessing missingness in data. So what we have to do is we have to reduce our data to a usable data set. But we also want to have the most data possible, right? So the best approach is really select a model that can do this for you. So models that can use penalization terms like lasso. You'll see L1, L2 regularization. Those are penalization terms. Lasso is great. It'll drop variables that are really not useful for your model. In pretty much every machine learning model, you can look at variable importance scores. You can train your model and then look at the variable importance scores and then rerun your model with just a subset that are kind of the most important variables, these types of things. But again, at the end of the day, we're creating a black box. We don't know what's in the box, except it's a model that we trained on some data. And we're going to put new data to it, and we're going to get some prediction on the outcome. We have to be very, very, very careful here. And we'll talk about why in just a few minutes. All right, so now we want to talk about causality a little bit. So causal inference in machine learning. Now, causal, colloquial use here. This is not causal like we mean in epidemiology. We're not looking at the Bradford-Hill criteria or any of this type of stuff. What we really mean is treatment effects or measures of association, risk ratios, odds ratios, absolute risk reduction, these types of things. Certain new machine learning methods actually let you extract those treatment effects. Causal forest is one, and I'll show you an example of this. And the coolest part of it is it lets you do this across subgroups. So you train one big model, and then you can actually look at subgroups in that model to get treatment effects. I'll show you how a use case for this. When we don't have the limitations like sample size and false positive rates and these types of things in machine learning as we do in frequentist stats. So here's an example. We did this study several years ago when I was at the University of Louisville, looking at oseltamivir, Tamiflu, for the treatment of hospitalized patients with lower respiratory tract infections. That's acute bronchitis, exacerbation of COPD, or community-acquired pneumonia. Hospitalized patients with flu. Now, problem, is we saw this pretty big difference. I mean, this is pretty huge difference, but not significant. So our conclusion is our conclusion. This is a randomized trial. This is what it is. Oseltamivir plus standard of care did not reduce clinical failure. Clinical failure here was like this composite endpoint of death and not getting better by 7 days and a bunch of different things. So patients came in, they got randomized to either standard of care for their LRTI or they got their standard of care plus Tamiflu immediately. And this was actually the days before essentially everybody got our nasal swab for every virus in the world when they came in. So we didn't know if they had flu or not right away. And that was the problem that we had and why we had such a big issue enrolling our sample size is that during flu season, it's only about 18% of patients with lower respiratory tract infection actually have influenza. But we had to randomize everybody and enroll everybody because we had to give them oseltamivir right away. And it was 3 flu seasons long. It was supposed to be 1 flu season long. Like you can imagine the inflation of the budget every year. And it would just so happen that we had 3 really mild flu seasons. And it just was a bad time to do this. So what we did then was took those data and used causal forests to estimate the treatment effect of getting Tamiflu versus not on failure, not, right, across a bunch of different subgroups of patients. So this is kind of getting more towards trying to get personalized medicine. It's not personalized, it's still subgroups of patients, but you're getting closer. So this figure here is kind of a dot and confidence intervals. So this is the treatment effect, would be the risk difference of whether patients had more clinical failure or less clinical failure. So what we took is these 80-some subgroups within our single model, our causal forest, and looked at the treatment effect. What was the risk reduction if that subgroup of patients got oseltamivir or not? And you can see like HIV, although this is what 60% less clinical failure. With Tamiflu, it was not significant. And you go down here, and the only one of these that was significant were the patients with influenza, and that's what we want, right? Because oseltamivir only works for flu, right? It's a neuraminidase inhibitor, prevents viral exit from the cell after the virus has been replicated in the cell. And what we see here is we have this 30–40% reduction in clinical failure if you got Tamiflu versus if you didn't, which essentially matches what we saw in our original trial as far as that risk reduction, except in our trial it wasn't significant because of the methods we used. Now we use machine learning and it is significant. So these methods are still in their infancy, but we're starting to see more approaches like this that may be actually better because of the lack of having to deal with sample size issues. All right, so we're gonna end this now. So where's this going? So automation. I didn't talk a lot about model selection because it's becoming kind of a non-issue. We have packages, free open source packages that work in R and Python and on their own, like H2O, Google's Keras TensorFlow, and other frameworks that really automate everything. You just give it a data set and it'll even split your training tests, select the models, look at every model, combine them together. You still need to make your own variables. You need to give it a data set that makes sense. And this is how it works. Here's an example. So this was a model I did several years ago I faked the data here, but this is trying to prevent no-shows in clinics. So, just not too many variables actually. And I have this H2O package in R, and I say, here's my features. X is just a subset of features in the data set. And then what's the outcome? What's it trying to predict? It's trying to predict this downsampled no-show, yes or no. I give it my data set and I say, I want to run it for 20 seconds. It's a great thing. You just tell how long you want to run and then how you want it to evaluate your metric. And then it'll spit out the output. So with this, I actually got it about an 81% accuracy at predicting no-shows with these 4 lines of code. That's pretty sweet. Now we can also use explainers. So we take this black box, but sometimes you want to know, like, why did this model predict this outcome for this individual patient? And you can do that. So explainers like DELX and Lime is an example, not necessarily traditional epi, but is a data set of survivors and non-survivors from the Titanic. And it's going to predict whether or not you survived or not based on these data. And you can see here, so individual patient data. So it predicted 57% chance of survival. And then you can look over here at this and say, what were the individual variables in the model that drove that prediction? Here you can see it was female sex in the title, and then a little bit of age group being between 25 and 35 predicted survival for this individual. And you can kind of look there. And this actually helps with trying to, evaluate if a model is becoming very biased in ways that we don't want, which we'll talk about in a second. This, the biggest issue in machine learning, and why everything is not automated. Because we don't measure everything, and we don't measure everything perfectly. These are computers recognizing patterns. They're not people thinking about the reality of life, which is why we don't have AI. Models can become very biased very quickly without very strong thought going into the models. And this is why you see in the news all the time, Facebook creates this model that becomes, starts spouting racist stuff because it was trained on Reddit threads, or Microsoft has a bot that says, whatever, because it was trained on, it saw patterns before in Twitter data or whatever, just random stuff. So we have to be very, very careful of this. And you can see, if you have a data set, you say we're trying to predict no-shows, and we have a data set that, just has, poverty and race and segregation and all of those things in the area that our data are coming from are very spatially segregated. In all of those things are associated with things like not having transportation or having a lot of jobs that you can't get off of. The model can say things that aren't what you're wanting at all. They become racist, and they become classist, and they become all kinds of different things because of the patterns that it saw, because of the data that you gave it to look at. All right, so a couple of additional reading materials. I can give some more. These 2 books here, Hasey's and James, these are free open source books for machine learning, statistical learning, that are just really, really great resources for anybody who's looking do kind of more of this. So that's where I'm going to end this now, and we leave us about 20 minutes for Q&A.
Great, thank you so much, Dr. Wimkin. Yes, we have had a number of questions roll in, so I'm glad there's plenty of time. Appreciate that. So I've, in some cases, traditional regression models, I've seen them outperforming machine learning models for the same question. Could you explain why this might be the case?
Yeah, it's probably, I would imagine it's case dependent, but a lot of times it has to do with how you've tuned the hyperparameters. A lot of those publications, they don't do the best job of tuning the machine learning part. Obviously, there's usually very little to do when you're creating a predictive model with like logistic. You just, here's the data, here's the output, whatever. And machine learning, you need to tune it. And a lot of those studies, they end up using just the defaults for whoever created the package, and that's, it's going to give you probably not the best output. But yeah, there can be a lot of reasons, but that's a common one that I've noted.
Great, thanks. So I know in randomized trials, the issue of sample size is crucial and important. One, especially finding power and kind of evaluating type 1 error rates. So I was curious. We had a number of questions kind of related to that topic. So I guess first is calculating power or sample size, is that an issue in machine learning? What is a large sample or a good enough sample size?
Yeah. There's people that talk about it, but for the most part, because you're not kind of locked into the frequentist idea, and this is actually really difficult it was very difficult for me when I was like transitioning to like more data science to combine the machine learning and statistical frequentist statistics and stuff and Bayesian, that we're so trained to be focused on, you have to have the sample size because of type 1 error, type 2 error, all these different things. Machine learning is not that. It's different. So you have to like shut that part of your brain off when you're dealing with ML. It's strictly patterns. So the sample size is dependent on how good your training data set is. Do you really have all the patterns in this training data set? And a sample size calculation can't define that. It has to be based on your knowledge of where the data came from, what the variables are, what the patterns look like. Again, if you're trying to create a random forest for, genetically modified mice to predict, whatever, antibody level for whatever, those mice are all pretty similar. You probably use a pretty tiny sample size because you're going to see all the patterns very quickly. Where if you're looking at, a heterogeneous population, across the United States or globally, you're going to need a much bigger sample size, because for the computer to see all the possible patterns to be able to generalize out to the testing data set, you're going to need a big training data set to have all those patterns in the data. So I wish there was a better answer for it, but it's part of, I'll throw it in the art part of ML.
Great, thanks. So we've had a couple questions asking about the issue of confounders. There's a obviously big issue in traditional methods. Are issues with confounders prevalent in machine learning methods?
Yeah, it's kind of similar. It's not so much confounding. It's just the variable needs to be there for whatever pattern that variable has with the outcome. So however that variable is distributed among all the other variables, it needs to be able to be there. So it's not confounding in the sense of, you're getting a false association or a missing association because the variable wasn't there. Actually, it's kind of more like the other one. If the variable is not there, you've missed the ability to see the patterns and how they relate to each other. I think the cooler part of ML, especially decision trees, like random forest or cat boost or XGBoost, is the effect modification. Because we're always interested in stratification. How do you deal with effect modifiers? Like, if you look through the literature, probably, like, essentially nobody deals with effect modification. They just throw the variable in there. It's confounder. That's close enough. We'll just throw it in as an independent variable. In tree-based models, the variables are selected in an individual tree with replacement. So you might have age selected as a variable, and it'll automatically find a cut point for that age. So let's say we have continuous age, and it selects less than 55 greater than or equal to 55. And then it selects gender, and then it selects, congestive heart failure. And then it selects age again, but this time age is 75 plus and less than or equal to 75. So effect modification becomes a non-issue in tree-based models, which is kind of nice. But I think this is one of the potential solutions, mid-range solutions for this unmeasured data, biased data situation. So when you're training your data set, you might consider creating multiple models. Stratify your models based on variables that could be problematic in your predictions. So if you think poverty is distributed in such a way that you're not going to be able to measure all the important data like transportation and different things like that, then you probably need to stratify your models based on poverty status or different quartiles of poverty or something like that, and then create 4 or 5 different models for each of these quartiles of poverty.
Okay, thanks. So you kind of alluded it to the kind of the black box nature of machine learning models. I was curious, is that, or we had some questions that were posed. Did these present any issues with explaining the predictions to stakeholders? They might be familiar with the traditional regression models, but not necessarily with machine learning approaches.
Yeah, it's very difficult, especially if you're. I mean, you can imagine like a physician who's sitting in an office and, or actually let's take an example of like an intensivist who's, they build some new model into their electronic health record to predict sepsis. I mean, as soon as all those data elements get input into the EHR, then maybe a pop-up will say, this patient is at whatever risk for sepsis. Usually the physician's already going to know. Like that's one of those things, like you look at the patient and like you don't need this model to predict this. And the fact that it's this, usually the explanations of like what variables went into the model and you're telling someone with a lot of experience and who can essentially diagnose the patient by looking at them to believe the computer when they know nothing about what went into this, and usually not even anything about machine learning or other than that it exists. So it becomes extremely difficult. And that's where some of these explainers like DALX and Lime can become useful, because then you can look at the individual patient and say, okay, this model predicted that this patient was going to have this outcome, and this is why. These are the variables that were in the model, and these are the variables that were driving this model to predict this particular outcome for this particular patient.
Great. So is there a particular scenario or use case in which machine learning should be preferred over traditional methods and vice versa?
I think not necessarily. Generally, if you're really trying to explain something, right now I think traditional methods are still generally superior. Like if you want a risk ratio or odds ratio or rate ratio or hazard ratio or something, traditional methods are probably going to be your way to go. Now, machine learning is going to shine in really 2 general areas. One, when you have a lot of nonlinear relationships between variables and the outcome. Traditional methods, there's some that work when you have these nonlinear relationships, but not like machine learning. Machine learning really shines there. And also when you have tons of data, and that's what we want to try to do. And you want to have more data, but again, more data that aren't just noisy. Things like, even if you have individual patient level data, you can always find some geographic identifier. For example, if you know the patient's home address or the county that they live in, you can get their county level Federal Information Processing Standard, FIPS geographic identifier code, And then you can go to the US Census, you can go to the county health rankings, you can go to CMS, and you can link all of these aggregate data elements to the individual. And now you have so much data that a traditional method is just not going to be able to handle that appropriately. And then machine learning is really going to be, depending on the model you select, obviously, it's going to be probably a vast improvement.
Thanks. Getting a number of questions all rolling in. Hard to keep up, but let me keep trying. So a couple questions relating to kind of multiple tests. Are there, does machine learning assist with that method? I think you might have alluded to that earlier in terms of the less reliance on the frequentist, I guess, paradigm.
Yeah. Yeah, you don't really have that. That's just not part of how everything is created. So you have this big, for example, let's take a random forest, for example, a very common approach, and this would be almost the same for XGBoost or CatBoost or something. You have your training data set, and the way the random forest is going to work is it's going to take a subset of that training data set, 2/3 of it about, and it's going to create decision trees. It's going to select a subset of about 7 or 8 columns. That's one of the hyperparameters, how many columns you want to select. And then it's going to say, let's create this decision tree. Select this variable, cut it at this, and then blah, 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 blah. How do we classify at the end? And it's going to do that like 10,000 times. So you're going to have like 10,000 trees, each one with different variables that are an option to be selected, again, with replacement, and a different 2/3 of the data. And then it's going to take that extra 1/3 and run it back through each tree to get it's called the out of bag error rate. So then at the end, it's going to say which trees were good and which trees were terrible based on this extra 1/3 being kind of our internal testing. It's looked at these patterns all the time, but it really has nothing to do with error. It has everything to do with pattern recognition. So it's not used any of these mathematical concepts of that we're used to seeing in frequentist stats. So it really doesn't. None of that stuff applies for the majority of ML models.
Great. So machine learning methods are employed frequently with observational data. Do they offer any assistance or any advantage with data that might come from a randomized trial?
Yeah, I mean, the example that I gave with the causal forest was from a randomized trial, and that's causal machine learning is actually much better suited for random data because there are some assumptions in those models, unconfoundedness, different things like that. And the alternative, for example, causal forest has an option, actually a separate model. It's called instrumental forest. So you're using an instrumental variable. If you're familiar with instrument, like from economics, they use instrument variables a lot, and two-stage least squares, regression types of things, where you've essentially created this variable that pseudo-randomizes your data. So if you're going to do a causal forest with observational data that's not randomized, you actually have to use instrumental forest and not a causal forest. And then if you've ever tried to find an instrumental variable before for the pseudo-randomization, it's like next to impossible. It's so hard. So yeah, there's issues like that. But as far as other models go, you don't have to, I mean, just as powerful for observational data as for randomized data. So again, because you don't have the sample size issues, these types of things can be a great additional analytic approach for your sensitivity analyses for whatever publication you're going for.
Right. And I guess, yeah, that you had mentioned it. We were referring to the colloquial term of causal. You don't. I guess the question is, you don't mean that in the same capacity as like a causal from like a randomized trial or.
Yeah, exactly. Yeah, it's not. We don't mean the consistency. What I'm gonna remember my Bradford Hill criteria from 20 years ago.
For some more. So a couple questions on composite outcomes. Is there any particular utility or capacity machine learning to address those sorts of sorts of outcomes?
Yeah, I mean, a good use, I mean, I guess a good argument for a composite endpoint like we did in our flu study is if you have a really rare outcome, it can be tough. I see actually a recent comment in the chat here, like what do you do when your outcome is like ultra rare? That can be super, super hard. So you can create a composite endpoint to try to increase that prevalence and then downsample. Smote sampling is actually is pretty useful. And I think there's some other more novel techniques even than smote. So I usually recommend doing it multiple ways. The traditional there's upsampling that I didn't mention because essentially no one uses just general upsampling. Upsampling is going to take the minority class. Again, if you have like this brief example of a binary endpoint where you have a rare less frequent outcome and a more frequent outcome, the minority class and the majority class, you can just copy rows in your minority class to increase the frequency. And that's kind of, it doesn't work so well. So you can downsample, but again, if your outcome's super rare, you're going to end up with like, nobody in your data set. So then smote sampling can be very useful.
Question about combining machine learning and traditional approaches. So for example, maybe using machine learning for feature selection and then a logistic or Cox model for odds ratios or hazard ratios is this approach, I guess, has had some criticism for not being interpretable. Can you comment on any of these approaches or pitfalls with this approach?
Yeah, I would say combining them can be really useful. And there's always like this gray area of like what's machine learning and what's traditional. Like if you do a regression model with lasso penalization, like is it machine learning? Is it not? Like there's a pretty wide gray area of of the difference between the two. But yeah, you can use. I've several times used like random forests or different things to look at variable importance scores as another additional method of variable selection. So you might, you could always use whatever backwards stepwise regression. I don't recommend any stepwise, but if you are forced into it, use backwards. And then use these variable importance scores from a machine learning model, use lasso, use ridge, use elasticnet, some other things, and then kind of look at where all of these, what variables did all of these different methods identify as important. And then if you find that every model that you do finds the same variables important, that's telling for you to be able to use those variables to go forward. So it's not just use one thing, but use a host of things and then look at the overlap.
Great. Well, I think one more question. What excites you most about the future of machine learning and epidemiology?
I was definitely not trying to keep up with it. There's a lot going on. There's a lot going on. I really, really, really like something I didn't actually mention here. That's also one of these kind of gray areas is natural language processing and text data. I think the utility of machine learning models for text data that's the next revolution. And we already see things. I mean, there's models that are trained, like example BERT. I forget what it stands for, bidirectional encoding of something or other. It's this pre-trained model, machine learning model that was trained on like the entirety of Wikipedia and the entirety of Google Books. Like it has everything. So this is how like Google knows what you're going to type when you're trying to type. These types of things are really going to change epi when we start seeing the transition into this. I mean, right before I left academia, we had been working on using BERT in the vaccine adverse event reporting system and the free text fields there. Like, how can we use this free text to try to create a faster VAERS, a faster reporting system, other than having individuals try to go through and classify things in the Medra dictionary. And that type of thing applied to electronic health records, physician notes, results from diagnostic tests are really going to be really going to be fantastic.
Great. Well, thank you so much, Dr. Wimkin, for the excellent presentation. And thank you to everyone who participated in today's webinar. On the Mind the Gap website, prevention.nih.gov/mindthegap, you will find several resources for this talk, including the slides and a list of references. We will also be posting a recording of today's webinar on our website in a few weeks. You will receive an email with a link to the recording when it is available. Thank you and have a great rest of your day.